Okay, welcome back. This is another calculus video, this time on a selected problem from problem set 1-4. This time we're looking at problem number 7, a slightly more tricky one, I think, so I decided to choose it this time. It says, for the definite integral of f of x equals, and then it gives us an equation, negative 0.1 x squared plus 7 from x equals 1 to x equals 4. First of all, sketch the region corresponding to the integral. So I'm going to go ahead and throw it in my grapher. Let's see, negative 0.1, oops, 0.1 x squared plus 7. It says from 1 to 4, so I'm going to change up my window to show us from 0 to 5 so we see the whole thing. Hit graph, and that's what we want to see. So technically we want to see from here to here. So I'm going to go ahead and sketch a graph of that. My graph went from 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me double check what it looked like. Looks like it starts at 7 and drops down to about 4 by the end. Alright, starts at 7. I'm going to select a different color for this. And it's going to drop down to about 4. So it does something like that, although more curvy. And we want the region from x equals 1 to x equals 4. So we want this area. Now, it wants us to approximate the integral by finding t10, t20, and t50. So, it's going to take a bit of work, so let's go ahead and start cranking it out. Whoops. I don't know why it slid over like that. So let's go ahead and do t10, and then we'll quickly go through the others. So t10 is going to equal, let's see, if we broke up a width of 3 by 10, it means that every triangle is 0.3. So 0.3 times 1/2 of the first, and then plus all the intermediates, dot dot dot, and then 1/2 the last. Now, how do we find 1/2 the first? Or sorry, how do we find the first, all the intermediates, and the last? Well, I'm going to go ahead and go back in here. We are starting at 1, and this time we are counting by 0.3. So my first right here has a height of 6.9, and then you can see the rest. So 6.9. 6.831, 6.4, I probably should have had more room for this. 6.639, 6.516. Going to start listing them out, because we know we're just adding them all up until we get to the last one. 6.375, 6.216. I need to scroll down. I'm about halfway done. 6.039. 5.844, 5.61, and our last one is 5.4, which gets the 1/2. So So now all we have to do is do all this addition times 0.3. So I'm going to go and bring up my calculator and start typing it all in. Now be careful as you type it in, or else a small mistake is going to ruin all that work. So 0.3 times 0.5 to the first, then add up all the intermediates, 6.831 plus 6.7, I can't remember what that was. I think it's 49. It's not going to make a huge difference if we're timed it off on that. Plus 6.639, it'd be no different than a rounding error. Plus 6.516 plus 6.375 plus 6.216 plus 6.039 plus 5.844 plus 5.631 plus half of 5.4. I just want to glance, make sure it all looks right. Make sure I don't have a decimal or a plus in the wrong spots. Looks good. And the parenthesis, and there we go, 18.897. So T of 10 is 18.897. Now, T of 20 and T of 50 are going to be found the exact same way. It just takes a lot longer. Now, we're not going to go ahead and do that for every single one. That's something that's pretty simple to do on your own. However, I am going to go ahead and copy down the answers from the back of the book for this part. We have T of 20 is 18, again, which isn't that surprising, 0.898875. 898875. And then we have T of 50 is 18.89982. 18.89982. Now, it makes a lot of sense that they're all very, very close to each other. And that the higher this number right here goes, okay, the higher the number of trapezoids you have, the more exact your answer is. If this were infinity, it'd be perfect. Okay, it looks like this is converging, which means it's going to become 18.9, because we have 18.897, 18.898, 18.899. Looks like it's slowly converging at 8.9 or 18.9, which we see in part C if you read ahead a little bit. Now, part B also asks us, do these values overestimate or underestimate the integral? How do you know? Well, sorry, this is part B. Well, let's just think about this. This curve, if I had graphed it better, it curves up and then down. Our integrals, our trapezoids, are not quite exactly the line, but they're not over it. Now, if the curve looks something like this, then we're going to have the possibility of having trapezoids with an area above the curve. In this case, it's below the curve, therefore we know it is underestimating. Now, the exact value of the integral is 18.9. How close to T10, T20, and T50 come to this value? Pretty darn close. Okay, 18.897 is 0.103 off. 18.898 is 0.102 off. And 18.899 is about 0.101 off. Let's see, how many increments n do you need to use until t of n is within 0.01 unit of the limit? You have evidence to suggest that t of n is within 0.01 units of 18.9 for all values of n greater than this. Now this would take quite a lot of work as well, but you pretty much have to assume, if we look, 10, 1.0 or 0.103, 20, 0.102, 50, 0.101, it's pretty slowly getting up there. Now it's not going to rise very fast. Okay, so we basically just want to assume that it's a lot higher value than. The book tells us that it's about, let's see, 7.01 units away um, from the exact answer. Okay? Now, most of what we just did is higher than that, which is even more exact, which is fine. Okay? But this gives us the idea that if we want it to a certain accuracy, we pick the number that best suits our needs. Now, we don't want to do more work than our accuracy requires, but if we need it incredibly accurate, we're going to need to have a very high number there. Okay, most of the rest of the problems in this section follow along the same logic using that trapezoid rule. So if you need help on others, just ask.